when we speak about the Curry-Howard isomorphism. So I guess it's not going to be clear for most of you, but that's really not an issue because the example for today will be a very simple one, just division by 2, just to make sure that everybody's on the same page. So we just, dividing by 2 is super easy. I try to subtract 2 as many times as I can here until I reach 0, 1, and then I'm done. And every time I can actually, every time I can retract something, I can retract 2, I will just keep track of that with the first one. So that's basically how the division works. And here's just an execution of that. Computation of the division. In our case, we try to put as much as possible of the logic in the types. That's the goal of this talk. No tests, no things like that. If we want to express properties, we put them in the type. So the first thing we do, we need to control, the data type. So instead of just using ints, we use nats. That's a very common encoding of nats using piano arithmetic, where you have basically the case 0. Here it's just D-O, and the successor case. So that's how you would write 0, 2, and 5. And just for convenience for the rest of the talk, it's not very important for NAT itself. I just have an implicit conversion. That means every time I see an int and I actually want to see a NAT, where I can just consider it's actually okay. And of course, only defined when the integer is more than or equal to 0. Okay, so the data type itself is not enough. We need to compute now. So plus and multiplication are easily defined by recursion on the left operand. In the case of plus, basically every time I can I find an S, on the successor on the S operand, I would just put it in front so that at the end I have extracted all the S's and I get the 0 case, and I just have to put that in front of M and I'm done. In the case of multiplication, well, it's super easy. It's just the fact that n times n is just m plus m plus m n times. So recursively again, I try to every time I find if I got 0, then I have the successor. I transform that on a plus, and I call myself recursively. Really nothing fancy. Just for convenience of writing, just defining some syntax, plus and multiplication, and the way to, the inverse of the implicit conversion, going from nat to int just because it's easier as human to process the results. Okay, I need somebody to help me with the being mode. Sorry, it's not my laptop. Apparently, it's. So just some useful computations so that you see that everything works as expected. Really nothing fancy. 2 is just S of O. 3 the same thing. 5 can be defined as the addition of 3 and 2. 6 as the multiplication of 3 and 2. And that's an example of going from nat to int. So now let's define what we wanted to do, the Euclidean division by 2. That's more or less the same idea as before. I had to do pattern matching just to see if I need a 0 or 1 case, or n plus 2. And I had the opportunity to call myself, so that's exactly the same code. You see the same thing as before, it's just that I iterate on nats, and just for printing, pre-printing, I'm using the 2 ints so that we can just see the right results. But that's definitely not enough, because now if I wanted to check that my implementation was fine, well, how would you do that? You would write some test, and you say, okay, does it work for 0, 1, and I try with 10, 1,000, I use property check, that kind of things. But it doesn't express the fact that I have some properties properties on the computed value, and there is a strong relationship between the input and the output. And everything can be expressed actually using this type. So this, you have to really understand that for the rest of the talk. That's pretty important. So here, I'm just saying y itself. So that's why I really want, but that's not enough, because I need to tie some properties between x and y. So that's the property that can be checked at runtime, which express the fact that x can be divided by 2 and the result is y. And it only works if I multiply y by 2, and I may have to add 1, basically I'm back to x. So you can actually see that it works in that case. 3 times 2 plus 1 is really 7, so I can actually construct a value for that type. 0 and 0 easy. But if I claim that 10 divided by 2 is 3, actually at runtime I would have an error. So I guess you understand where I'm coming from now. I'm saying at runtime I have an error. And that's the thing I don't want. But okay, we'll see how we can do that. First, let's see how we have to express that. We have to update the Euclidean division. Instead of returning just the NAT, I want the NAT with the property. That's the thing that I need. But that's basically the same thing, right? I just need to, the only tricky thing is when I call recursively myself, I need to extract the y so that I can use it with the plus 1 here. But I'm still constructing a div. So that's clearly not enough. So there will be nothing complex here. You can trust me, but I will need to use the Coq proof engine, and don't worry, it will be super easy. So what is Coq? I guess most of you don't really know what this is. So that's just an environment where you can speak about mathematical properties, theorems, and proofs, that kind of things. And the system is such that you can, it will be able to check your proof, and at the end, it will say, okay, does it work? Yes or no? No, well, you're stuck. Yes, cool, we can do something with that. And just like language, Coq would come with a standard library where you have actually a lot of theorems and functions and data types already defined. And it's much more powerful than your everyday language, in that it's actually based on the higher order type and calculus. And we'll see where it's useful, but basically for today it would be using dependent types. Well, by the way, the name Coq is actually a plain word coming from C also, in case you were wondering. Okay, so let's do the same thing in Coq now. Inductive, in this case, it's basically what we did before. It's just a generalization of algebraic data types. But you recognize the zero case, the successor case. Coq would actually give us a few other things for free to reason about the recursion. We won't really be using that, but we can check the type of some NATs here, and we see that everything type checks just the right way. After the data types, of course, we need to define some functions, plus and multiplication, exactly the same implementation as before, just the syntax is just a little bit different, and we define the plus at the same time as an infinite operation, but nothing really special. Same for multiplication, and I was checking the type. Here I can actually compute. Hopefully you can compute things, otherwise it's not really useful. But now, that's where the big difference will be. I was complaining that div2 was not enough to express the relationship between x and y. Here I can speak about a type. So this is a type that depends on x, right? So div2 itself is not enough. It depends on x. X can be given, so I can speak about something that can be divided by 10, for example. And the way to construct that, so that's my constructor. Again, it's a generalization of the algebraic data types. That's an inductive construction. So dynamics would be my case. And in order to construct a div2 x, I need to provide a y. That thing, I will come back on that. And then at the end, actually, that would be the only way to construct that. But actually, that's not enough. In order to construct that, I need to give a proof that the relation between x and y is actually okay for this property. But that's static again. So when I reason about that, statically, I need to provide a proof. So let's see some examples. So I'm just checking the type x of 1. So here I'm just binding x to 1. And you see that the check is, oh, that's something that is still waiting for y and that thing. Okay? So what kind of y can we provide? We can provide 0 because we expect that the division of 1 by 2 will be 0. And still something expecting the proof. So I need to give a term for the proof so that I can actually finally construct the final type. Okay. I want to explain that. So here you can see the proof itself. It's something that normal humans are not really able to give just right away. So another approach for that is actually to use the interaction mode. So that means that you start with a theorem or something that you want to prove, and a lemma, a theorem, or whatever, and you tell Coq, okay, let me interact with you and help me go to the final word. So here I'm saying, okay, can I actually, for all math, construct these two of text, which in our case again means being able to provide a y such that the disjunction is actually correct. So now we have this, we start interacting and we say we have to prove that, and what will be above the line will be the context. So we just remove things from the context so that we can use, just like in math, and we try to modify the goal. So here in that case, a general case when you say for all x something, it's the same as saying given an x, let's prove this something. So it's just introducing the for in the context. So that's what I'm doing here. So and by the way, so that's the record, just like in Scala. So I'm interacting with using the command line, and now you see that x is part of the context. So I will go through the proof. It's not really important that you understand all the details. At the end, we have the full script of the proof, and it will be reason about it. But the only thing that we need for the proof itself, I don't know if you remember in school, when you prove properties on natural numbers, you say that, to prove that the property is true for all n, you say, oh, let's prove it for the 0 case, and then let's say it works for n, and I will prove the same thing works for n plus 1. And if you have the two cases covered, then you can deduce it works for all n. Well, this is just something a little bit more powerful. It means that instead of just doing n plus 1, I will say for everything, given something, an n, if the property is true for all the n that were actually less than this n, and if it's true for 0, and it's not n 0, then I can deduce it's actually okay for everything. I don't have to prove that. I mean, it's already part of the standard library. It's called GTWFREC, and I can actually use that. So I will need that. Just trust me, it's actually there. So I'm just introducing that, saying, well, it's actually proving my stuff. It's actually proving I can just assume that it works for everything that is actually below n. So for any n that is below n, I can assume that I was able to extract a y. So that's basically my recursive case, right? I'm somewhere, I can look at any number that is actually less than me, and I can find a y. So I can use that, especially it will be useful for the case n minus 2. But first, we need to deconstruct the n, just to see if we are in the case 0. So here now we have two sub-goals. We had the goal n is equals to 0, and n is actually n plus 1. So now we have to prove that for 0. Well, there is nothing really difficult. Proving that means, again, providing a y such that the division is okay. So 0 divided by 0 works. So I'm just constructing a proof using divets, providing 0 to divets. But in order to really use that, I still have to prove that the disjunction is fine. And in this case, it's fine. I mean, as a human, you see 0 is really equals to 2 times 0. So I can just go very quickly. I choose the left operand of the disjunction, and then by reflexivity, 0 really equals 0. So nothing really fancy. And I'm left with the goal n plus 1. Again, that's not enough. We know that we have to do that twice, on the case 0 and the case 1. So we do it again. Now we have to do the same thing for division by 2 of 1. Again, the corresponding y is 0. So I'm going very quickly. The right operand, it's easy to prove that the disjunction is valid. When you have special cases like that, it's always super easy. And I'm left with the case n plus 2. That's why it's actually very interesting. And now I can finally use my the hypothesis that I did at the beginning, for the n minus 2. So this is basically, this is, if this is n, this is the n minus 2, right? So that means that if I look at that and I take, the m is actually this guy. Here you see the n plus 2, and if I say n here, I can find a y. That's the cool thing. So that means from h, I can find a y and put it in my context. So that's here. And now, I still need to prove that. But I can reason by case, and I have to do it for the two cases. It's not really difficult again. So here, if you look at that, and again, you have to provide a y such that it works. Well, if you look at it, the y plus 1 is actually the right solution. Because then if you multiply by 2, and if you need to you add 1, you're back to the n plus 2 case. So that's what I'm doing. So now I have a lot more things in the context, and I have to prove very simple equalities. So I guess you can, if you look very quickly, you can see that those two things are basically the same thing. And Scala is able to, Coq is able to do that very quickly. So we do it for this one, we do it for the other one. At the end, we have just the last goal, from using the hypothesis. That's the last thing that we need to do. And at the very end, well, I'm done. So it was not very difficult. So that's the entire script for the proof. And let's actually focus on what we did. So the thing that's not highlighted, it's just normal interaction with the proof, modifying the context, nothing really fancy. What's highlighted here is actually the meat of the proof. So using the way, so using GTWM was just a way to do the recursion. Here, induction and the second type is just a way to deconstruct the input. Here we are just providing the value to finish the proof and say that everything is fine. Here, this is where we use the recursion. So that's basically using the fact that I can call myself and with n minus 2, and I can get the y, and I can actually construct the final value for the proof. But if you look at that, the way I explain the proof itself is really about constructing the value. So that's very much, it feels very much like a program. Well, it happens that thanks to, that's basically what Curry Howard is all about. There is an isomorphism between the proofs and the programs. And it happens that you can actually mechanically extract a program from the proof under some conditions. So here I'm just saying, hey, extract actually the corresponding code for the Euclidean division, which was actually defined as a theorem with a proof. Actually, from the proof, we are back to that. So there are two interesting things here. We are saying, wow, look at the type for div2. A few things actually disappeared. It's like Coq was able to see that the property was knows really about computation. So it's really not useful to keep the non-computation part at runtime. We just want the computation itself. So Coq was actually able to remove all the unwanted stuff. And the final code is here, and it looks very, very, very much like the first thing we did. So everything works well, except that actually Scala is not really a target language for code. And so somebody tried to do, a Japanese guy made code to Scala. It actually breaks the extraction altogether, and I really didn't have time to fix that. But if you look at the OCaml code that was extracted, it was, I mean, it was just replacing the words. You can trust me. You can try that yourself. And that was exactly that. It's it's basically replacing word by word. There is nothing special. And with that, I'm done. You can find the full proof and everything at this URI. And I'm happy to take questions.
If you prove your program of your thesis, you have a group which is a program, but does it give a program which is feasibly usable? Can you say that it doesn't generate a very awful program? Because for this example, it seems to be working out well.
Yeah, I mean, it works well because so that's a very valid question. Given a specification, you always have as many ways as you want to actually implement the specification. That's the same thing for a proof. And you know that for any different proof, you would have different corresponding program. Actually, in some cases, the extraction doesn't work very, very well, and the kind of programs you get are actually not really useful in practice. In practice, people don't really use, just to go a bit further in the explanation, people don't really use the extraction from Coq, and they use Coq using more like the functions that I defined at the beginning, and then they would use dependent types here. So you would have the pure computation in the function being defined. The dependent types would generate some proofs that you still have to construct, but at least you have full control over the computation that you want to achieve. That's usually what people do. Here I went for the proof just for the sake of this implementation, but that's not usually what people do. Yes?
Okay, so very short question.
Anyway.
So has this technology and Coq and Bertails been used for proving anything useful? I mean, some real proof that what was invented, and then they use software to find the proof.
Yeah. I realized I didn't choose my mic. Okay. So yeah, questions about what is useful? Yeah. So for example, that kind of things is used for Java applications embedded on your cars. So that's used a lot just to make sure, for example, that two programs won't be able to, one program won't be able to access the memory for the other program, which is usually nice when you have financial things being involved. There is a very, very big project that is writing a compiler for C, actually fully written in code, putting all kind of properties on that. That's really useful because now, if you have proven, if you have some code in C, embedded code, for example, for a train, a plane, and you prove some properties on it, and wow, you've been working on that for very long, and then you compile the C code to assembly language, and the semantics of the assembly language is not respected, in the transformation, then that's useless. So having a compiler that is fully proved is very, very important in that case. And there are a few other examples.
Yes, just to add an example, there is recently an example about proof about SSL protocol invariant, and the researcher who did the proof with Cox found that most of the current implementation of the SSL libraries were not checking the proof, and he found security on thanks to this kind.
Yeah. So yeah, that's another approach. Yeah, you have a host language. You generate some proof assumptions, and based on this language, because you have a model for it, and then you try, and you have other properties, and then you try to see if they actually match.
Thank you very much.
Okay.